Hello everyone, and thanks for joining me today again at Cyber Llama Talks. And today we have a really interesting topic. Before talking about process emulation, we really need to understand how CPU emulation worked and why anti-malware products had to migrate from simple CPU emulation into process emulation. We will start as always with the malware. This is a very simplified picture of the malicious binary file, MZPE. Let's say it is a polymorphic one. So it has a polymorphic cryptor, and we cannot just simply apply a signature on it. Instead, we need to emulate it. And as I thought before, even between 2000 and 2005, we already had CPU emulation technology. So we need to emulate it to unpack the first layer. For this, I'm going to split the space here. So this one is the file itself. And this one is going to be our CPU emulator memory space. To emulate binary, we need a few things first. We need a virtual CPU or vCPU. And this one contains all the registers, such as EAX, EBX, ESP, EBP, all that you probably know if you reverse engineer or look at the malware, know x86 assembly. Also contains flags, which are needed for branch instructions, and a bunch of other things, right? I'm not going to go into all the details what vCPU would contain, because it's pretty much the emulation of the CPU. Even though the emulator called CPU emulator, to really emulate something, it needs more than just vCPU. It also has a stack with a stack pointer where we can push the data and then pop the data out, right? Push in and pop out. So it means when certain instruction executed, such as push EAX, for example, it would push the value of the EAX onto the stack and pop would pop it out. And so on, right? It's very necessary to be able to emulate it, to have emulated stack. And the last but not least, it's a VMM, Virtual Memory Manager. And in very simplified view, what it contains is a source virtual address and target virtual address. And let me explain what it means. We have a binary file on the disk. It's not executed, we're just going to emulate it. But of course, this binary file, if you actually try to execute it, will be loaded into a virtual memory, and it will have what's called image base. It's a virtual address into which this executable expected to be loaded. And for 32-bit executables, at that point of time, this address would be something like this. If it's executable, it would most likely not even have a relocation table, so loader would always load it into this image base. But of course, that if you actually run the binary. However, we're not running the binary, we're actually running emulator. We're inside the emulator memory space. So we need to map the binary into our, from its source addresses, right, the binary it expects, into a target, which is emulator process. And so what's going to happen, it's going to be mapped page by page into this virtual space, right? And for example, this source address is going to be mapped to this one, and this table would be showing it, right? It means inside emulator process, to access value which is lying somewhere in the source binary under this address, you're actually accessing that address, right? So it's like a simple translation table, and it's just more like all the pages here. Those are three main elements which any CPU emulator would need to emulate. But how emulation process actually works? It always starts from fetching, and what it does, it looks up an entry point somewhere here, right? It parses the header, and it says, okay, where's the entry point? And it starts to fetch bytes out of it. So it reads certain number of bytes, and it pushes those bytes into disassembler. Disassembler would interpret these bytes, understand these bytes, and convert them into instruction. And so when instruction type is detected, it will call specific interpretation function or interpretation routine. So for each instruction, that's A, B, C, D, and so on, you would have a different interpretation routines, and so on. After interpretation is done, it would update EIP, it's a pointer to the current instruction, and the loop will start all over again. That's a very simplified explanation of how emulation works. So what happens again, so we fetch bytes, disassemble them, look up the routine, and when the routine is executed, that one actually updates the CPU, updates the stack, updates the VMM, right? And those one all emulated ones, right? It's not real CPU, not real stack, not real virtual memory, it updates those structures inside interpreter routine, and depending on instruction, for example, if we interpret instruction push EAX, interpreter routine would update the stack. It would push EAX value into the stack, and it also would update ESP here to reflect that the address has changed of ESP. When we push in the stack. So, and if that's another one, for example, move x0x40, for example, that would again, it would update EAX here, would move the 0x40 into it, and at this point nothing else happens, just going to update EAP after that. And another case would be a jump instruction, right? In this case, it would just update EAP itself, so it can be a part of the interpretation function as well, the updating EAP, or if it's not a branch instruction, it can just update EAP based on instruction size. That's how CPU emulation works. You would say, okay, we can emulate instruction by instruction, we can unroll all these encryption layers and see the original payload, right? Not that simple. Let's see why and what kind of problems CPU emulation faced. While CPU emulators were quite a powerful technology, while fighting malware, and especially polymorphic malware which used server-side polymorphism, they faced multiple problems. First of all, CPU emulator have no idea about API and syscalls, meaning if in the middle of the code you have instruction which calls create file, CPU emulator doesn't know what to do. It would just crash because the create file inside the import data would not be resolved. It would be just a pointer to the string. Similar thing would be if it would find an instruction like a syscall inside the call. Since it does not really have awareness about how to emulate kernel or what kind of syscalls are available, it again would not know what to do. It can skip the instruction and try to continue emulation, but then for malware it's actually very easy to check if the syscall or API function call was successful or not. So because CPU emulators didn't have any awareness of it, a simple API call would pretty much bypass or crash CPU emulators. Another way to bypass CPU emulator would be to try to access process environment from the code. When binary is loaded and process is initialized in Windows, there are certain user mode structures which are created by a loader and initialized during the initialization of the process, such as process environment block and the thread environment block. And those contains a lot of information about what modules are loaded inside the process, what variables are available, the process environment variables, what command line is, and so on. It's actually possible to access those structures pretty easily through the instruction by accessing, depending on operating system, I believe if it's 32-bit, that would be through FS, segment, to access PEB. And at that time, of course, it was only 32-bit, mostly 30-bit operating system, but also in 64-bit, that would be GS. You can simply write a command move that value to EIX, for example, and that should move the address of PEB inside the process. Of course, CPU emulator is not aware about any of these structures, so if malware would try to access it, CPU emulator would not know what to return because it's not really aware about process environment. Another trick to bypass CPU emulator is to access an exception handler. It also accessed through FS GS special registers. The Windows supports two main exception handler types. It's a structural exception handler or SEH and vector exception handler. Yeah, and they both rely on certain process environment. And again, malware can purposefully throw an exception and build this SEH in advance to trigger execution of the instruction it wants, while the emulator might not properly emulate an exception handler and just fail altogether. So that would be like pretty typical ways to bypass CPU emulators. Of course, there are others, and I would just mention them here, but they're not going to be solved by process emulation. However, they still existed, and specifically it would be slowness. As you see on our previous slide, it's pretty complex process of fetching, disassembling, looking up the table, and then interpreting each instruction. So the performance might go from 10 to 100x slower per instruction, depending what instruction is doing, if instruction accessing memory or not. It also incorrect emulation. While it's easy to emulate simple instructions like move EX or something like this, there are some more rare instructions which, besides doing the main purpose, might set certain flags, and a certain combination of instruction might set or reset certain flags in CPU. And so if emulator is not aware about this, the malware can check those flags and execute incorrect branch and just crash if it executes under emulation. And of course, system environment, that was not that much used at that point of time, but I just want to mention it. If process tries to do any other inter-process communication, let's say it tries to open the handle of another process or read memory or inject code into another process, I mean, in CPU emulator, concept of process just doesn't exist. So it would fail for sure. And even process emulator would struggle if the malware tries to do some tricky things with the systems, maybe creating and reading the file or creating network connections and so on. So, but definitely process emulation will be a step forward. Anyway, those are the problems CPU emulator had against polymorphic malware. Let's see how process emulator solved those problems and how process emulator worked. Thanks for watching today's episode about CPU emulators. Hopefully now you know better how exactly CPU emulators worked for emulating polymorphic malware, but also know what were the weaknesses of CPU emulators which actually allow polymorphic malware to bypass them. In the next episode, we're going to talk about process emulators, which were the next step in evolution of the emulators for anti-malware, and how exactly process emulators help to emulate polymorphic malware or malware in general, and not just bypass the encryption and polymorphic layer, but also allow to detect behaviors of malware and introduce this new class of detection, which is behavioral analysis and behavioral detection. Stay in touch. I hope to see you in the next episode. Don't forget to subscribe and share. Thank you very much. See you next time.